So the seventh experiment is estimation of toughness properties of steel. The aim of the experiment is to draw the calibration curves of the machine used and to find the impact values of the standard steel specimen using Izod test and Charpy test. We are using the equipments, a very impact testing machine, setting gauges for the specimen, and the steel specimens for conducting Izod and Charpy test. Now coming to the term toughness. Toughness is a measure of energy that a material absorbs during plastic deformation before its failure under impact load. So this depends upon the strength of the material and its ductility. So ductile material possess higher toughness values compared to brittle materials. The impact value that we are measuring using the equipment available in the laboratory is a measure of the toughness of the material in terms of the energy required to fracture the specimen under dynamic loading. The toughness is dependent upon the testing conditions like temperature, velocity of impact, size of the specimen, and the method of fixing. So lower temperature means the material will have lower ductility and hence low impact value. Then speed of loading, when it increases, low toughness value is obtained. And dimensions of the specimen also affects the toughness value. Larger dimensions, that means that will result into lower toughness of the material. So there are two types of tests usually conducted to measure the toughness. One is the tensile impact and the other one is the bending impact test. We use impact bending test in the laboratory. This is the sketch of the machine that we are using for conducting the experiment. So this is called the impact testing machine. So the different parts, we have a dial. So the measurement that we are taking in the lab is the angle. Angle means the angle at which the pendulum or the hammer, that is before impact and after impact. So when a hammer of significant weight, which is kept at a position, we know that it possesses potential energy. Then when it is released, it will hit on the specimen that is kept at the bottom portion of the machine here. It will be kept. So they're fixing, depending upon the fixity, it can be either cantilever or beam test that we conduct in Izod and Charpy respectively. So that will hit the specimen and the specimen will be failed. So the needle or the pointer in the dial will give. So before the impact, we can measure what is the angle at which the hammer is kept initially, and after releasing it, it will hit and some energy is lost for failure of the or fracturing of the specimen. Then after that, the hammer will have some energy possessed. Because of that, it will rise to another position which will be lower than the initial energy level, and we can measure the final angle also. So this bottom portion shows the setting gauges for the specimen, and two levers are visible in the figure. The right side, the lever is used for adjusting the specimen gauge, and the lever provided on the left hand side, that is used for operating the hammer. So this is the photograph of the machine available in our laboratory. So this is a machine, it's a simple machine, but at the same time, so we should be very careful while dealing with this specimen, machine, because this hammer has got a weight of 24 kg. And when it is kept at a height, so it will be possessing 17 and 30 kilogram meter of energy. And when it is released, it will hit. So when we are standing, etc., we should be a little bit away from the machine so that the hammer is not causing any damage or accidentally. So though you should be very careful while dealing with this machine. There is no protective cover for the hammer. In some machines available in some other colleges, I have seen that there is a protective net provided so that we will not go nearer to the machine, and that is a safety measure that is not available with this machine. So coming to the dial, so we have a 2-pointer. For that, the graduations are angles. We are measuring the angles in degrees. then we have two pointer. So one is the main pointer and the other one is the dummy pointer. So when the machine is set, we will keep the two pointers together. So when as the hammer is lifted or raised, automatically the actual pointer will rise along with that, and that will come to a stop when the hammer is set there. Now we will keep the dummy pointer here also along with the main pointer, and then now when it is released, finally we can measure what is the angle of the hammer after the impact. So this is the specimen that we usually use for conducting the Izod test. It is a cylindrical specimen of circular cross section, and almost a length of the, see here, two notches are provided. See, this specimen actually consists of two parts. It can be used for two tests. That means when we hold the specimen will be held down here. So it will act as it will be kept as a cantilever, and at the bottom it will be hold, and this top portion here, the hammer will be strike and the top portion will be failed, and some portion will be remained that can be used for another test also. Okay, so we are providing this notch on the specimen, for the stress concentration, and it is provided usually on the side where the tensile stress is developed. This is the specimen for Charpy test, which is a square in section, and we are keeping this specimen as a beam. That means the two ends of the specimen is supported, simply supported on the support provided on the gauge, and we will be applying a central point load. That means the load applied is impact, and here also we are providing a notch. The notch is so provided that it comes on the tensile side of the specimen. So this is the setting gauge. So here see the setting gauge. Here the setting gauge is for the Charpy test. Here these two are the simply supported supports, and we will keep the specimen simply here, and the load will be applied from this side. And when we are applying it, we know that when a load is applied to a beam, it will bend. So it's a flexure like a test. And when we apply load from this side, so the beam will bend in the sagged position, and the tension will be developed on the side away from the hitting position. So we will keep the specimen in such a way that the notch is coming on the reverse side, where the hammer will be hitting from this side, and the notch is opposite to that. So this lever is used for changing the gauge setup. So we can operate the shown lever, and you just pull it in the towards the right, and this gauge setup will be loosened, and we can remove this one, and we can add the attachment for the Izod test. Since our machine is not working for a long time, so when I visited the lab, it is not possible to change the gauge setup, and they have to do some trials and make it possible. So the lever is not working condition now, so it could not be changed, and I cannot show the other setup. See here, the operating of the lever is like this. So just pull it towards the right side, and then now actually it should loose, and we can remove this one, and the setup for the cantilever or the Izod test can be fixed. So the Izod test is nothing but the central portion will be this left side portion will be removed, and we will add to some which is similar to the one that is available here. And there will be a central hole, and we will keep the specimen into that. The cylindrical specimen will be kept into that, and will be fixed and locked by the same lever. Okay. Now, for the machine to set in the Izod and Charpy condition, we have two slots available on the back of the machine. So here it is written Izod and Charpy. So this lever can simply take and just keep it into the bottom or the up. The top one is the Charpy position, and the bottom one is the Izod position. This is only a mechanical arrangement. By keeping this lever in the Charpy position, when the hammer is raised at this position, it will be locking to a slot, and the hammer cannot be removed without operating the lever. And when we just change it, just pull it and keep it in the down means the hammer can be lifted to a position which is available for the Izod. That is a simple arrangement. So this is the specimen details that is used for the test. We have the square and the the circular cross section. So we usually use circular cross section or a circular rod for conducting the Izod test in our lab, and the square cross section specimen is used for Charpy test. See here, the notch is provided. The dimensions are shown here. See the notch position. So we have a total diameter of 11.4 millimeter, and we are giving a notch of depth, say 5.3 millimeter, and this is provided at a specified depth from the top of the specimen, that is around 22 or 28 millimeter from the top of the specimen. So this is the specimen for, so here where the hammer hits, that striking position is also shown here. The hammer will be striking on the top portion. See, because of this one, it will bend towards this side, so the tension will be developed. So it is a hogging condition, bending. Just like any cantilever bend, when we apply an end point load, so it will bend in a particular fashion. The same way the specimen will bend, that means the tension will be developed on the side where the hammer hits. Whereas this is the Charpy condition. The Charpy test, the specimen is kept in the as a beam simply supported. See the load application direction. So we are applying a load. So one more thing is there, the striker. So the striker that we are using for striking the specimen has got two ends. One is a flat end and the other one is a triangular end. So this for conducting the Izod test, we are using the flatter end, whereas for conducting the Charpy test, we are using this triangular end of the so that we can change in the hammer. Within the hammer, it is just screwed, and we can loosen it and change the position according to the test that we are conducting. Here the load is applied as a central point load with the impact loading using the hammer. So this is the schematic diagram of what is happening when we are doing the test. So for calculation purpose, we are using a very simple equation. We are finding out what is the energy loss when we conduct the test. See here, this is the line sketch of the machine and the hammer positions. So this shows the free position of the hammer. The hammer has got a length of L and its weight is W. So when this is in the free condition, there is no potential energy for the hammer. Now for conducting the test, what we are doing is we are lifting this hammer and keeping it to this initial position. See here, this angle phi1 shows, that can be read from the dial. The phi1 represents the angle at which the hammer is kept when at the beginning of the test. So it will possess a potential energy which will be equal to W into H1, where H1 is the difference in the elevation between the initial rest condition and this raised condition H1. So H1 can be represented in terms of L and phi1. So this inclined length L is the length of the hammer, and when we take its vertical component, it will be cos phi1. So this distance will be cos phi1 and the total distance is L. So the value H1 will be equal to L minus L cos phi1. Now the initial energy possessed by the hammer is equal to WH1. That is equal to W into L minus L cos phi1. We can write WL into 1 minus cos phi1. Now, after hitting the specimen, when it is released, it will hit the specimen kept here, and some energy is absorbed by the specimen during its plastic deformation, and the remaining energy will be possessed by the hammer, and it will come to a next position, say, which is H2 distance from the free position. That is, H2 will be lower than H1. So the final energy is equal to W into H2. That is equal to W into L minus L cos phi, where phi is the angle of rise of the hammer after the impact. Now we can calculate what is the energy loss. This energy loss is represented as the impact value or the energy that is absorbed by the specimen during its breaking. E1 minus E2 is equal to WL into 1 minus cos phi 1 minus WL into 1 minus cos phi. So you subtract WL into, you expand and cancel the similar terms, and we will get finally WL into cos phi minus cos phi 1, in which W is the weight of the specimen, weight of the hammer, L is the length, then phi is the angle after impact, and phi 1 is the initial angle before impact. So the calculations are very simple. We are using only this equation that I have already told. So first of all, either we can read the initial angle from the dial and the final angle also from the dial and calculate the energy that is or the impact value of the specimen. And even without reading the initial angle also, we can calculate the phi 1 value, that is, for our machine, the initial energy possessed by the machine or the hammer when it is in the Izod position is 17 kilogram meter, and for the Charpy position it is 30 kilogram meter. So once we know E1, we can calculate the phi 1, and for the both the conditions, E1 is equal to, for Izod condition, E1 is equal to 17 kilogram meter, and W is equal to 24 kg, L is equal to 1 meter, get the value of phi 1. We are getting some 73 degree, 21 minutes or so. And for Charpy, the initial energy is 30 kilogram meter, the W 24 kg, and L is equal to 1 meter. We can calculate what is the value of phi 1. It is something around 104 degree. Now, what is meant by calibration? A calibration chart means for any machine, the calibration chart represents when we take unit measurement on the dial gauge. So what is its corresponding load value or energy value? That is the calibration curve. So when we plot for different divisions of the machine and the corresponding measurement that we are taking. So in the case of a UTM, the measurement that we are taking is the load. And when the needle moves through one single or a single division, what is the corresponding load taken? That is called, that is will be obtained by plotting the load versus the number of divisions in a curve. We will get a calibration curve. From that, we can get what is the load corresponding to any number of divisions for on the dial. Similarly, for the impact testing machine, the readings that we are taking is the angle, and the value or the measurement that we have to get is the energy loss or the impact value. So we know that what is the equation? Equation is energy loss equal to E1 minus E2 is equal to WL into cos phi minus cos phi 1. Okay. So in which cos phi 1 is a constant for Izod test and the Charpy test. Then only unknown is the phi value. Now what we are going to do is, for different values of phi, that means 0, 10 degree, 20 degree, 30 degree, calculate the value of this energy loss or impact value and plot a curve. So this is a tabulation that you have to make. So in the equation, WL into cos phi minus cos phi 1, phi 1 value we got from this calculations. Now for Izod, we have a phi 1 value of some 73 degree, 21 minutes or so. You can get it accurately. Now for phi is equal to 0, WL into cos 0 minus cos 73 degree, 21, what is the value? Then 10 degree, 20 degree, 30 degree, like that you go on substituting the values of phi and get the energy losses. Similarly, the energy losses for Charpy. For Charpy, we have the phi 1 value still higher than the Izod value. It is around 104. So these values will be different. So both the columns you complete. So Izod will have the values up to this column only, because after that the complete energy is lost by the hammer. Then for the Izod value, so it will be up to the last column will be there. Now remaining are the actual measurements that we are taking. So we are reading the angle. So we can do, we can read the angle from the dial, then calculate directly. So that is what is shown in the right hand side. Angle phi. So here it is taken as a phi 2. So it is only after the impact 5 value only. ഇവിടെ 5 നമ്മൾ യൂസ് ചെയ്തുകൊണ്ട് ഇവിടെ 5 എന്ന് എടുക്കുന്നേ ഉള്ളൂ, just to distinguish between the actual measurements that we have taken and for plotting the calibration curve. So the angle that we are reading directly, get the energy loss using the same equation WL into cos phi minus cos phi 1. Instead of that, you substitute phi 2. Then you will get the value. So if you are doing a number of tests, you take the mean value. Here we are doing only once, so you report the value. Similarly for Charpy also, we are measuring the angle and calculating the energy loss. That's all about the procedure. Now for calculation purpose, you can use these two values. For Izod, the directly measured value is 48 degree, and for Charpy, the directly measured value is 72. These are phi 2 values. Okay, so this represents the shape of the calibration curve that you will get. This is only for your reference. The copy adikanda, so you have to fill up the table and do the calculations, and using so phi on the x-axis you plot, and you plot the energy losses on the y-axis. Then you will get two curves. So finally, what is shown here as the dotted line is whatever value that we are reading from the dial as 48 degree. So you project it to the Izod curve and get the energy loss. Similarly, 72 degree, if it is 72 degree, you plot to the Charpy curve and get the energy loss. Okay, that's all about. Now let me try to display the video. So this is the video. A small stretch only is available. So this is the dial gauge. Now see here how the reading is taken, that is given. See here the pointer, both the pointers have kept it together. Okay, now the lever is lifted, or the hammer is kept at the Charpy position. Now it will be 0. Both the pointers are kept together. Okay, now the attachment is changing to Charpy. And now you can see the striker inside, that is fitted here. See here. See, this is a flat edge and this is the triangular portion. So here we are doing the beam test. So triangular portion is facing the specimen. See here, the slot is kept as Charpy. Okay, now the specimen is fixed, that is why the lever is towards the left side. Now this longer lever is used for operating the, see here the beam is kept. So the notch will be towards this side. The striker will be hitting here. Okay, now just, okay. Now the hammer is released, hit the specimen. See here the pointer is now here. So now we can read what is the angle from here. So the graduations are simply degrees. You can directly take the measurement. So in order to do the Charpy test, the changes that we require is you change first of all the slot. The back, on the back the lever is lowered to Izod position. Then the hammer can be lifted to only a height lower than that of Izod. Then change the specimen and its attachment, fix it, then release the hammer. And so also we have to change the striker condition. The striker face should be this flatter one, and release the hammer and break the specimen. Similarly, you take the angle measurement. So that's all about the experiment. Then if you have any doubt, now you can ask me. Did you follow the experiment? Have you got any clarification? So So from the PowerPoint, I will be uploading to Classroom, and there I have given the angle values that you have to use for the calculation. Then the calibration curve will be similar for all. Okay, so you have to calculate the energy losses for the different angles, then plot it. Okay, it's a simple calculation.